glad you're here because I was asked by the organizers, who I thank very much for the opportunity to speak here, to also summarize the plethora of results that were shown at ICRC. I should point out, I have 15 minutes. There were 25 contributions. In the end of my slides, there's a list, and you can click on the link, and you can see all the talks. So I'm giving this behalf of the DAMPE collaboration, and it's about the first year in orbit. So let's get started. Let's see if this works, and it does not work. All right, just a second. Okay, never mind. So I'm just gonna do it this way. So in case you really have to leave, I encourage you to stay, of course. The takeaway messages are DAMPE works really well, and expect to have some exciting results coming soon. The results I'm presenting today are mainly confirming what other experiments have seen. So I'm going to talk about the launch detector design and give you a launch video, actually, then talk about the on-orbit performance and delve into the results afterwards. So first is the launch, and instead of showing you a bunch of slides, I'm just going to give you the launch video, and there's some details shown here on the bottom. So we launched from somewhere near the Gobi Desert on December 17th in 2015 on one of the Chinese rockets, and there's also no audio. Not sure what that is. Yeah, okay, sorry, there was supposed to be a bang. So we're taking off here. You don't hear the Chinese people talking there in the back. You'll see soon the disconnect from the second stage. So we're climbing, and everything worked really beautifully. The Chinese have the best rockets. So we're disconnecting there, and the second stage is here now shown, and there you have the birth of DAMPE as it being released into the orbit. We're operating at an altitude of about 500 kilometers with an inclination of 97 degrees, and it's a sun-synchronous orbit. This orbit allows us to pass it in a period of 95 minutes, as well as to get a data rate down to about 16 gigabytes per day. So it's significant, but we also read out a lot of channels. We have a mission lifetime of at least 3 years, and we turned on HV on December 24th, and our Christmas present was a 300 GeV electron candidate. I'll talk more about the detector. Also on the same day, just a few seconds later, we have a 1.3 TeV carbon candidate. And I'll tell you more why we believe that this is carbon in just a moment. All right, the dark matter particle explorer, or short DAMPE, has 3 main goals, and I don't have to introduce these to this audience, but obviously it's the question of the particle dark matter identification. Here in particular, what's interesting is the identification, or is the sensitivity to spectral features. Here I show an example of gamma ray line annihilation, and there was a nice talk by Mariangela yesterday in the plenary about why dark matter indirect detection is important. What the takeaway here is that in case you want to point at the galactic center versus our orbit, they are basically more or less the same sensitivity, and that's after 3 years. The other theme is cosmic ray acceleration and propagation. Particularly, we can measure charged particles, such as electrons. And no worries, this is just a simulation, so there's nothing seen here, and I'm not going to talk about the cosmic ray electron results today. What I'm going to talk about are protons, helium, that we can measure up to about 100 TeV, and we can thereby say something about what AMS sees, what Khaled might see in CREAM, but at a much better sensitivity and a much better much lower systematic uncertainties. Last not least, but my review here is a little bit biased towards gamma ray astrophysics. What we can do is we can look at the gamma ray sky, and it's a high energy gamma ray sky. So this will bridge the interface between GeV to TeV observations in the age where CTA is coming online. How do we do this? We have an instrument design which looks fairly similar to what we have from Fermi, for instance. So you have a top anti-coincidence shield. In our case, this is a top shield, which is made of plastic scintillating detectors it both acts as a veto for charged particles, but for charged particles, we can also measure the Z as looking at the deposited energy, and that allows us to discriminate against different ions. Then we have about 6 layers of tungsten interleaved silicon tracker converters. That allows us to measure the tracks of incoming charged particles, as well as pair conversion. And then we have the main feature, which is a 308 crystals, hodoscopically arranged bars, and by far right now the deepest calorimeter ever to be deployed in space. So this is massive with 32 radiation length. The total detector is about 1 nuclear interaction length. And in order to even improve the proton to, or the hadron to electron gamma separation, we also have a neutron detector on the bottom that detects the delayed neutrons. The energy resolution is better than 1.5% above 10 GeV. Keep that in mind. The expected performance is detailed in this paper, and I encourage you all to look at it. Just the highlights. It's an instrument that goes from 5 GeV to about 10 TeV at an energy resolution that's unprecedented at these energies in space. The energy range of protons and heavy nuclei is somewhat higher, so about an order of magnitude higher, with the energy resolution being somewhat lower. The effective area, for those of you who hope to do gamma ray astrophysics, I have to a little bit disappoint you because it's about a factor 10 smaller, but the instrument is a lot smaller. Nevertheless, we can do interesting things. So the on-orbit performance, just to give you an idea, the trigger rate it varies between 20 to 200 hertz. And unlike other experiments, we actually take data within the South Atlantic anomaly where our rate goes up the highest. And as we cross 20 degrees in latitude, we run calibration runs. What you see here, instead of having a lot of technical plots, I show you the data rate as we take it from the 27th of December all the way up to June when this plot was made. And it all doesn't have really any hiccups, so we've been working really well. And you can see we actually have quite a few events above 5 TeV, so that's about a couple dozen per day. We have about a lifetime of 18.4 hours per day with a 3 millisecond dead time. The acceptance, for those of you who want to do projected sensitivity estimates, electrons is a really nice acceptance that goes up, is about 0.3 square meters per radian. Which flattens out all the way out to 10 TeV. These are some pre-flight estimates. We're working on calibrating that exactly. These are estimates from the photons. The photons have two features. You have a turn-on curve due to the trigger efficiency, and here backsplash takes over, so we're trying to improve this. And as far as cosmic rays go, they are about a factor 10 less. Again, there are plenty of contributions at ICRC, which I encourage you to take a look at. So on to results. That's gamma rays first light. Not quite first light. It's after 510 days, and it's the sky map after above 510 days above 2 GeV. We get about roughly 200 gamma rays per day. That's not quite what Fermi can do. But for those of you who do gamma ray astrophysics, you recognize the galactic plane, so a couple of sources. And for those of you who can squint, you see something down there. We did see CTA 102. We did also see the massive flare, and that's probably the first time you heard about gamma ray astrophysics was DAMPE, because we had an astronomer telegram there. And you can look at the exposure map, and that explains why we can't see the sky the same way Fermi does. So the exposure map is highly influenced by the sun's synchronous orbit, and the sun's synchronous orbit has as a consequence that we spend about 6 times as much time to look towards these two spots with respect to the rest of the map. So we are highly non-uniform. We do cover the whole sky over the whole year a couple times, but not fully uniform. And the field of view is about 1 steradian. Nevertheless, you can discover pulsars, and by looking at pulsars, you can actually independently confirm that your photon selection is actually producing photons. So you look at these again, you pick the 2 standard ones, Geminga and Vila. They have different phases, and PSR J007 is here picked because that falls into our highest exposure range. You see the peak phases here, and these results match very well with what Fermi sees and also what Agilis sees. So we have a good idea that we're not completely off with what we're doing. Shifting gears, protons and ions. We use the plastic scintillator detector on the top, which deposits its energy, and you can look at the spectrum, and this here are the protons, here comes the helium, and then you keep going on to lithium and higher and larger nuclei. So this is our on-orbit spectrum after 1 year. Now you can, in this energy bin that I show on the top, now you can simply naively place a cut here and say, okay, these are your protons. Almost. What you see here is our simulations of our Monte Carlo protons and helium. Here overlaid the red one, the green one is helium, and the blue one are the protons. What you do see here, even in this scale, you don't need to go to a log scale. You see that the green leaks into the blue, so you need to do some template subtraction, and that's what we do when we calculate the proton spectrum. And the proton flux spectrum was already shown by Veronica on Wednesday. And what we do see, so this is based on 16 million events, about a year, we do see a hardening above 200 GeV. So we use these template fits to correct for the helium background. And I would like to invite you to the comment that this includes systematics and statistical uncertainties. So the systematic uncertainties are highly dominated by the trigger efficiency, and that's shown here on the bottom right. The trigger efficiency, what you see here in blue is actually the orbit data, and in red the Monte Carlo. We are currently more or less limited by the Monte Carlo that we've produced. Going up to very high energies, it becomes more challenging because you have to understand how you simulate these cosmic ray interactions at the highest energies, and we're working at this. But you see a discrepancy between orbit data and the Monte Carlo, and that causes these error bars to blow up. Now on to higher nuclei, we can look at the charge identification. And the charge identification we can do in two separate instruments. One is the PSD, that's the plastic scintillator on the top. This is the full spectrum, now measured actually as function of the charge Z. And I started labeling all the way from proton to nickel, but there are a whole bunch of peaks in between. Boron here, boron to carbon, so you can do this with a very good resolution. And the resolution is about 13% here, down to 32% here. And you can do the same thing with the SDK because we also have that information in there. And we have about 73,000 channels that we read out for all the events. So you can focus on these little boxes here and do essentially the same analysis. So you look at this, and this is the helium flux. On the top, I show the small plot of what I showed before. And what you see here is actually that the contribution from protons is effectively negligible, and the contribution from lithium, not shown here, is also negligible. So there we don't have as much challenges with the template subtraction. Nevertheless, the systematic uncertainty of about 21% is dominated by the trigger efficiency. So this is based on 4.4 million events. And again, we observe the hardening towards 200 GeV. So, and with that, I actually have to summarize already because we are hard working at it. It's a fairly small collaboration. We're trying to work on various aspects at the same time. We launched in December 2015, and I hope I convinced you that this is a new instrument. It's a new opportunity because it provides the deepest calorimeter in space, and that's going to be the state until China launches HERT on board of the Chinese space station in 2021. We had an incredibly short turn-on phase, which took only about 7 days. And since then, we've been practically working without any glitches, any significant problems. And we've been in nominal science operations since January 2016. We cover, despite being a small collaboration, we cover a pretty large scientific exploration program. I would say separately, two main themes. One is gamma ray astrophysics. We're still trying to fully define this. I have to say, from my own perspective, I thought I could do sort of Fermi science with DAMPE. Now I learned that I cannot really do this, and this will govern where we're going. But what I would really like to point out is the fact that we observe things that are very similar to Fermi and Agile is a confirmation that our instrument works. So once we do that, we can go to much higher energies. And I showed you here the flux plots, but the flux plots are truncated at 10 TeV, not because we don't have any events, but because we didn't want to show you anything beyond that. Expect to see some cosmic ray electrons results soon. I cannot tell you any more about this today. Thank you very much.
All right, so you're the only speaker this morning to end early. Impressive. Okay, although Dan was literally to the second, literally. Okay, great. Well, we've heard some, that was very interesting and good overview, and we expect more great things from DAMPE. Are there a couple of questions?
John over there. No.
So I find kind of hard to believe that you're going to do TeV gamma rays because I look at your map and you say you have 200 events per day at 2 GeV. So you're going to see 1 TeV gamma per day.
That's certainly correct. And what I meant, or what I tried to emphasize, is as an all-sky instrument, we're not really that capable. Nevertheless, we have the opportunity to point. And the original plan was to run 2 years in survey mode and then move into a targeted observation mode. And I would say there we can certainly beat other instruments by simply staring at, say, for instance, the crab. And the crab, for instance, a colleague of mine, she's working on getting the crab pulsar at high energies. And it's really, we're getting there.
Nice results. You mentioned that the overall systematic uncertainty was at the 20% level?
Well, the largest contributor is the trigger efficiency. That's really the key systematic uncertainty that we have to deal with. The other uncertainties are sort of at the percent level. So in fact, we also looked at what happens with unfolding, and the unfolding results, at least as far as electrons and gammas are concerned, are essentially consistent with not even doing unfolding. So that's encouraging. And yeah, really the main uncertainty is the trigger. And that has to do also with the fact that we're testing some hadronic models at the highest energies. So we're trying to figure that out. But the limitation is really also on the computational side.
Should that be understood as affecting all bins equally, or is it bin by bin?
It's about a 21%. It goes somewhat down towards the highest, towards higher energies, and that has to do with the fact. Well, there are two aspects. One is we have 2 triggers on board. The first one is the low energy trigger, which we haven't been using a lot. The high energy trigger is what I've shown here. The low energy can give us a little bit more performance. The problem is the low energy is heavily pre-scaled. At the highest energies, we're really affected by this discrepancy between data and Monte Carlo that I showed. And yeah, I would say it grows in terms of trigger efficiency as function of energy, but there are other smaller other uncertainties that dominate the low energy regime.
Okay, sounds like you think that it could eventually be much less than 20%.
Oh, absolutely,
okay.
Absolutely. I mean,
look forward to it.
Yeah. And perhaps one last comment. I should say that I said I will not talk about the electron spectrum, but we do have a measurement of the electron spectrum starting from 50 GeV up to 5 TeV, which will hopefully soon be published. And there the systematics are at the percent level. And so there's not a single experiment out there that currently has the performance to beat us in terms of systematics at the highest energies.
Okay, let's thank Stephan again.